Today I'm going to talk about linear time algorithm for a minimum degree spanning tree. This is a joint work with my advisor, Duan, and my colleague, Haoqing. Suppose we are given an undirected graph, and we want a spanning tree that minimizes the maximum vertex degree in this tree. This generalizes the Hamiltonian path problem, since we can simply ask if the minimum tree degree is equal to 2. Thus, this problem is NP-hard as well. Therefore, to find efficient solutions, we have to tolerate approximations. Here is a brief history on this problem. In 1992, Furey and Raghvitri introduced a polynomial time algorithm with approximation delta star plus log n. Here, delta star refers to the minimum spanning tree degree. 2 years later, the same set of authors improved the approximation to additive one, which is optimal, and their algorithm runs in time mn. Our new algorithm has near linear running time, and it achieves 1 plus epsilon plus log n approximation. Let's first review the algorithm by Furey and Raghvitri. They uses a basic lemma which is called the witness lemma. The statement is the following. If the vertex set is partitioned into a sequence of subsets W, V1, V2 through VL, such that all intercomponent edges should touch the witness set, then we can argue a lower bound that delta star is at least L minus 1 over W. The proof is the following. Consider any spanning tree. Then it must have at least L minus 1 intercomponent edges, since it spans all subsets V1, V2 through VL. Now, since all these edges are incident on the witness set W by the pigeonhole principle, at least one vertex in W has tree degree at least L minus 1 over W. The basic approach by the algorithm is called local search. Suppose we have a suboptimal tree, and we want to improve its vertex degrees. If we find a non-tree edge UV such that both degrees are less or equal to d minus 2, plus the tree path contains a vertex with a high degree. Here, integer d is a parameter used by the algorithm. Then we can switch non-tree and tree edges to improve the vertex degrees. Look at the following picture. Label the vertices with their tree degrees in the spanning tree. After adding the non-tree edge and removing a tree edge, we can reduce the highest degree by 1. The main algorithm repeatedly finds tree and non-tree edge switches, and it terminates until it cannot do so anymore. In the end, we can prove that the maximum vertex degree in this tree is bounded by delta star plus log by applying the lemma with the witness set equal to the set of all vertices whose degree is at least d minus 1. Now let's discuss what prevents a linear running time. In the old algorithm, it repeatedly goes through all non-tree edges and finds edge switches. The bottleneck is that the degree of any vertex could possibly switch between d-1 and d-2 for many times, and therefore the algorithm has to check every edge for multiple times. For example, in this picture, there is a degree d-2 vertex at the center. Say at some point we have found an edge switch which increases its degree to d-1. After a second edge switch, its degree goes back to d-2 again. And in this case, we have to scan its adjacency list once more because there could be new edge switches incident on this vertex. Now let's discuss a linear time algorithm that computes a log n approximation. The previous issue is that adjacency lists could be scanned multiple times. So to improve the running time, our idea is that we force the algorithm to scan adjacency lists only once, even if vertex degrees could possibly drop below d-1 later on. Here's a linear time algorithm. Define S to include all high-degree vertices. Then we go over all edges, and if both endpoints are in different tree components after removing set S, and plus that both tree degrees have never been d-1. Then we would perform a switch on this edge with another edge on S. In this way, each edge is visited only once, and therefore our algorithm runs in linear time. Here is an example. Suppose at some point there is a degree d-1 vertex at the center. Then its incident intercomponent edges cannot be involved in any edge switch. Suppose at some point we have found an edge switch which reduces some degrees. Then, after this edge switch, its tree degree could be reduced to d-2. Thus, this would introduce more possible edge switches on this vertex. However, since our algorithm is lazy, it would not check these edges again. So, this is the main reason why our algorithm is faster. Because of the laziness of our algorithm, there is going to be problems with applying the witness lemma. Say, we take the witness set to include all vertices whose tree degree was once at least d-1. Using the witness lemma, we could argue delta star is at least L-1 over W. Here, L refers to the number of tree components after removing set W. Unfortunately, this set W could contain too many vertices with low tree degrees, and therefore the number of components L could be much smaller than D times W. And so we cannot relate delta star to this parameter D. Ideally, for those vertices with a low tree degree at the beginning, most of them may never reach d-1. For example, in this picture, only a small number of them may reach d-1. So hopefully, in the end, witness set would mostly consist of high-degree vertices. Now, what if most of them actually reach d minus 1? Say this vertex reaches d minus 1 at some point. Then, by the algorithm, it must have contributed d over 2 edge switches during the algorithm. And so the total degree of high degree vertices may drop by d over 2. So if more vertices comes to d minus 1, then the total degree of high degree vertices would drop even more. If most of them reach d minus 1 as well, then the total degree of high degree vertices would be reduced significantly. And therefore, in this case, the number of high degree vertices would be reduced greatly. And so the current spanning tree would be a low degree one. A remaining issue is what happens to vertices with medium degrees, let's say between d over 2 and d minus 1. For this issue, we try log n many different choices of the parameter d, and this could make sure that the number of medium vertices is relatively small. More specifically, we partition the axis equally into log n segments, and we apply our lazy local search procedures on each of the landmarks di, and we can prove that delta, which is the maximum tree degree, would be reduced multiplicatively. Now let's turn to describe our 1 plus epsilon approximation. The idea is called multi-hop switches. Basically, in our previous algorithm, each edge switch only involves one pair of non-tree and the tree edges. We can generalize this idea to include multiple pairs of non-tree and tree edges. For example, on the right-hand side, we could add both of the dotted non-tree edges to the tree and remove these two yellow tree edges from the tree. And this could reduce the highest degree by 1. So, to implement this idea, our algorithm searches for longer and longer hop, non-tree and tree edge switches, which is similar to the block and flow algorithm in the MaxFlow literature. Assume in each iteration we do not have switches with small hops, say less than k hops. And then we try to find k-hop switches. The first step is to partition the graph into k layers, and then we use a depth-first search. To partition the graph, we first collect all vertices with degree at least d, and then put them on the first layer. After removing the first layer, the tree is divided into several components. Since the graph does not contain two hop switches, all intercomponent edges must be incident on degree 1 vertices. Then we collect all of these degree d-1 vertices and put them on the second layer. So on and so forth until we have k layers. To perform a depth-first search, we start with an arbitrary intercomponent edge, and then find the tree path connecting both endpoints. Then we try to enumerate vertices on this tree path on higher layers. For each one of the vertices, we scan its adjacency list and look for intercomponent edges. And then we find tree path that connects to even higher layers, and then we do the recursion until we can reach the first layer. And this would give us a k-hop switch. We repeat this procedure until k is large enough. Then we can prove that either the tree degree is reduced multiplicatively, or we can try the witness lemma at each layer, which would prove that delta star is at least 1 minus epsilon d minus log n. And this concludes the main algorithm. Thank you.
So, if anyone has a question for Tianyi, please come to the mic in the middle of the room.
Can everybody hear me?
Yes, I can hear you.
Hi, Tianyi. So I have a question about the witness lemma. Is it true that delta star is equal to the best lower bound that can be obtained by a witness? And if not, are there any results about the gap?
So you're talking about the optimality of this witness lemma, right?
Yes, if it's like a characterization.
Well, I cannot recall clearly, but no, I'm not sure about it.
Okay, thank you. That's I think I can find it.
I can vaguely recall a statement that says, that kind of relates this delta star to something like to a certain value. Says if you enumerate all kinds of witness and you derive and you calculate this lower bound, and that says roughly equal. I'm not sure.
I see. Because maybe this has something to do with the problem being in co and p or something like that, because it gives you a lower bound, right?
I see. Oh, it's like you, it's like a witness, and
Yes.
it gives you lower bound on that.
Yes.
So
Okay,
are you trying to crack this lemma and trying to improve this lemma, and that may
no,
give you?
I just wanted to know if there is a gap, like when you have a gap like that comes from, say, linear programming and the actual results, or something like that. But yeah, but I'm not trying to do anything on it right now. I just that, yeah, I think it's a very interesting lemma.
Sorry to interrupt. We don't have time for more questions as the other talk will start, so we can ask more questions to Tianyi later. Okay. Thanks, Tianyi, for your talk.
Thank you.